This video is one of a series of videos I've made for students who are learning physics to prepare to enter a diagnostic medical sonography program. To find other related videos, please see my playlist, Physics for Diagnostic Medical Sonography Students. In this video, we're going to begin to talk about Newton's laws of motion, and there are three of them. So here we're going to start with Newton's first law. It turns out that Newton's laws have everything to do with forces. And so the first thing we have to do is figure out, what do we mean by a force? When we talk about forces, really what we're talking about is a push or a pull. So for example, let's say that I've got a block sitting here on the table. I could push or pull on that block and exert a force on it. And so you'll notice that when we exert a force on an object, it's not only an amount that we're pushing or pulling, but there's also a direction involved. And so force is a vector. We've talked about vectors before. A vector is a quantity that has both a magnitude, meaning a number, and it has a direction. So with a force, clearly both there's an amount and a direction that are important. For example, let's say I push on this block with a force of 4 newtons. And by the way, we'll talk about the unit of Newton, but that's our unit of force. So I'm pushing on the block with 4 newtons, but the direction matters. Am I pushing it to the right or am I pushing it to the left? And so force is a vector. The next thing that we have to understand in order to understand all of Newton's laws is to understand the concept of a net force. What we mean by the net force is the sum of all the forces acting on the object. However, we have to be a little bit careful here because force is a vector. So we can't just add the numbers. We have to think about which way the forces are acting. So let's look at an example. Let's say again I have my block here, and I'm exerting a force of 4 newtons to the right. But let's say I'm also exerting a force of 3 newtons to the left. Well, the net force then is going to be 4 newtons minus 3 newtons. So in other words, when the forces are in opposite directions, we're going to subtract them. If they're in the same direction, we would add them. So in this case, the net force would simply be equal to 4 newtons minus 3 newtons, or 1 newton to the right. You can imagine if instead I had a picture that said I've got a block and I'm exerting a force of 2 newtons to the right and then an additional force of 5 newtons to the right. That would be a net force of 7 newtons to the right. So that would be 7 newtons to the right. So now that we have a basic understanding of what we mean by a force and what we mean by net force, let's now look at Newton's first law. Newton's first law is called the law of inertia, and we'll define what we mean by inertia in a few slides. But it says a body will remain at rest or will continue to move with constant velocity in a straight line unless acted on by a net force. So let's see if we can understand the significance of this. Let's look at the consequences of Newton's first law. The first idea is probably the easier of the two to understand, and that is that if an object is at rest, then what Newton's first law tells us is if it's not moving, the net force on that object has to be equal to 0. And I think we can kind of understand that. Nothing's happening, the net force is equal to 0. The example that's a little harder, or the part of Newton's first law that's a little bit harder to understand, is that second part of it about moving. So once an object is moving, in fact, what Newton's first law tells us is no force is required to keep it moving. Now, that's probably not your usual experience in life. Because if you do something like take your pencil and give it a push on the table, after it goes just a little distance, it's going to stop. And that's because there's a force acting on it, which is friction. But in order to understand Newton's first law in this context, let's think about an example where there's no friction. So, for example, let's say that we've got some ice here, and we take a hockey puck and give it some initial motion along the ice there. We know that because there's essentially no friction, that puck is just going to keep going and going. And so the idea here is that an object that's moving with constant velocity also has a net force acting on it of 0. And we're going to go through some different examples just to make that clear. This thing that we've been talking about, that an object, if it's at rest, wants to stay at rest, or if an object is moving, it wants to stay moving, we call that property of matter inertia. So objects in general don't like to change their motion. In other words, if they're already moving, they want to keep moving. If they're already at rest, they want to stay at rest. That's what we mean by inertia. Let's talk about the concept of weight. Sometimes in everyday speech we interchange the word weight and mass, but they mean different things. Weight is the force of gravity, and the force of gravity is just the force that the Earth is exerting on an object. So your weight is the force of gravity, or the force the Earth is exerting on you. Well, let's use you as an example. Let's figure out what is the net force acting on you right now. Let's assume that you're standing. So here you are. Forgive me if this doesn't look like you, but there you are. And you'll notice that you're not moving. Well, what Newton's first law tells us is that the net force acting on you has to be equal to 0. Now, the thing to keep in mind is just because the net force is 0, it doesn't mean that there aren't forces acting on you. So in the case of you standing on the ground, there are actually two forces acting on you. The first is the force of gravity. In other words, if we use this dot to represent you, gravity is trying to pull you down. So we've got the force of gravity acting down. But the reason that you don't fall is because the floor is pushing up on you. And so the floor is exerting a force up. And what happens here is those two forces perfectly cancel each other out. In other words, again, when we add them, we've got a force up and a force down, and the net force is equal to 0. Let's look at a great example of the law of inertia, and that has to do with car safety. And specifically, let's look at the example of seat belts. So we've got our person here driving in their cool little race car, and this person is not wearing their seat belt. So let's see what happens when this person hits this barrier here. Okay, so they're not really paying attention. They're probably on their cell phone. And they don't notice there's this little red wall in the road. And they don't have their seatbelt on. What's going to happen? Well, you'll notice what happens, and that is the car gets stopped by the wall. But what happens to our person? Well, they don't get stopped because without your seatbelt on, there's nothing that helps to transfer the force that's acting on the car to a force that's acting on you. And so you go flying out of the car. And this is why we need to wear seatbelts, because otherwise, if the car stops and there's nothing to hold us to the car, our bodies want to continue to move with the same velocity they had before. And before the advent of seatbelts, this actually used to happen quite frequently in front-end collisions. People would go out through the windshield when the car stopped, but they needed to keep going. Let's look at another example. A car driving down the highway with a constant velocity. What's the net force acting on the car, and how many forces are acting on the car? So here's a key phrase you want to watch for. If I tell you something is moving with constant velocity, we know from Newton's first law that the net force has to be equal to 0, right? Because an object will move in a straight line with a constant speed, in other words, constant velocity, or stay at rest unless there's a net force acting on the object. So if the object is moving with a constant velocity, the net force acting on the car is 0. Now, again, that doesn't mean that there are no forces acting on the car. It just means that they all perfectly cancel out to 0. So let's look at an example of a car driving down the road and look at what are the forces acting on that car. So here's our car, and just to make sure you understand, this car is driving in this direction. So that's the direction the car is moving. And again, I'm just going to kind of draw what the forces are acting on the car. Well, first of all, the force that the engine exerts is trying to make the car go forward, so that would be the force the engine exerts. We know that if we're here on Earth, we can't avoid the force of gravity, so the force of gravity is pulling down on the car. And we know that a surface, like the floor, or in this case the road, is going to push up. And so the road is going to push up. And then there's a force to the left, which we'll call the force of friction. And this is actually a number of different forces present. There's air resistance, there's just the friction in the bearings of the wheels, etc. But there is that force that's trying to make the car slow down. So when you're driving down the highway at a constant velocity, all these forces are perfectly balancing out so that the net force is equal to 0. Now when we get to Newton's second law, we'll see what happens when the forces aren't balanced out. But in this case, any time an object is moving with constant velocity, the net force on the object has to be 0. And so you might know that when you're going down the highway with a constant velocity, that's when you get your best gas mileage. And the reason for that is the only thing your engine is doing is it's just overcoming the forces of friction that are present. So you're not trying to speed up, you're just overcoming the resistive forces that are trying to slow down the car, so they completely balance out and the car just continues to move with a constant velocity. Why don't you try this multiple choice question on your own? So pause the video and see if you can get it right. It says an airplane is flying at a height of 30,000 feet at 550 miles per hour directly towards Los Angeles. The force from the engines is 20,000 newtons. The weight of the plane is 10,000 newtons. What is the net force on the plane? Okay, did you figure it out? Well, the key here, like I mentioned in the last problem, is anytime an object is moving with a constant velocity, the net force has to be 0. So I'm just going to write that. Constant velocity. Anytime you see that, that means the net force has to be equal to 0. Now, how do we know this plane is moving with a constant velocity? Well, I told you it was at a specific height, it was moving with a specific speed, and it was moving in a specific direction, right? So those pieces of information tell you the plane was moving with constant velocity. Therefore, the net force has to be 0. But what about all these other numbers that I gave you? Well, if we look at the forces acting on the plane, it's very similar to the car. we have the force of gravity acting down, and in fact, we're told that. Remember, weight is just the force of gravity, so we're told that's 10,000 newtons. We're told that the engines are exerting a force of 20,000 newtons to the in the direction the plane is going, to the right here. But there must be two more forces acting, because otherwise the net force wouldn't be zero. Well, right now our plane is going to crash because there's only a force down on it. It turns out there's another force on an airplane which is called lift. And the shape of the airplane's wings is what provides an upward force called lift. So the lift has to exactly counteract the force of gravity for that plane to stay at the same height. Once again, we have what is often called drag, but I'm just going to call it friction. And that is, again, it's the frictional effects of air resistance. So if you've ever held your hand out the window of your car when you're going, fairly fast down the road, you feel how strong that air resistance is. That's a force of friction, and that would be keeping the plane from going faster. So again, when the plane is going at a constant velocity, the only thing the engines are doing is just overcoming that force of air resistance or force of friction. So the key thing is, as soon as you know the object's moving with constant velocity, you know the forces have to add up to zero. So we've said that the concept that an object wants to either stay at rest if it's already at rest or stay in motion if it's already in motion is called inertia. And what we want to do is now understand, how do we know whether an object has a lot of inertia or a little inertia? Well, it turns out that mass is a measure of inertia. So the more massive an object is, the more inertia it has, meaning the harder it is to change its motion. So you can try an experiment on your own with this right now. If you pick up something really light, like a penny, put it in your hand, shake your hand back and forth. It's very easy. You don't feel that it's hard at all. But now pick up a heavier object like a barbell or a textbook and try shaking it back and forth. And you'll notice it's much harder to change the motion of that heavier object. That's because it has more mass, and so it has more inertia. Another way to think about this is, imagine that you had to stop something coming towards you. If you had to stop something like a plastic ball, that would be easy. But how about if somebody threw a bowling ball at you? That's much harder to stop it because it has more mass, it has more inertia. Let's talk about what mass is. If you look in most textbooks, the definition they usually give is that mass is the amount of matter in an object. But what does that mean? Well, all objects are made up of atoms of different types. And so really the mass of an object is determined by the type of atoms that make it up and how many of those there are. So that's what we mean by the amount of matter in an object. We measure mass in kilograms or grams generally. I'll just remind you that the kilogram is the SI unit of mass. And that's a little confusing because normally you would think it would be the thing without a prefix, which would be grams. But in the SI system of units, the standard unit for mass is the kilogram. So again, what is weight? Weight is the gravitational force on an object's mass. Now, one of the reasons we can interchangeably, or we often interchangeably use those terms, is that the more mass an object has, the stronger the force of gravity. So again, if you're holding something like a penny, you can hardly feel it in your hand. It doesn't have much mass, so the force of gravity isn't very strong on it. Hold something heavy like a nice heavy textbook, it feels heavy because it has more mass, so the force of gravity is greater on it. We're going to always measure force in newtons, but I do want to just mention that in the British system, force is measured in pounds. So again, if you step on the scale in the morning and see your weight in pounds, that's literally simply telling you how hard the earth is pulling on you. Let's look at how to calculate weight from mass. The relationship between weight and mass is the following. Weight is equal to the mass, and that's got to be in kilograms, so I'll just mention in kilograms, times the acceleration due to gravity, which we talked about in a previous video. So remember that g represents the acceleration due to gravity. And that's just a constant here on Earth. If we went to a different planet or we went somewhere like the moon, the acceleration would be different. But here, it's just 9.8 meters per second squared. So let's do an example. How much does a 3 kilogram object weigh? So again, weight and force of gravity mean the same thing. I'm just going to use my formula. W is equal to m times g. And so the weight is going to be equal to 3 kilograms times 9.8 meters per second squared. Now, if you do the math, what you're going to get is 29.4. And notice what the units would be. They would be kilogram meters per second squared. But I've been telling you that force, or weight, is measured in newtons. And so in fact, we now know the definition of a newton. 1 newton is simply 1 kilogram meter per second squared. So that's the definition of a newton. And the key thing to remember is, as long as you put your mass in kilograms, and you put in the acceleration in meters per second squared, when you multiply them, you automatically get the weight in newtons. Let's talk about some related concepts. Sometimes it's easy to get confused among things like weight, mass, volume, and density. Let's talk about what volume is. Volume is the amount of space that an object occupies. And volume can be measured in liters or cubic centimeters, cubic meters. And remember, fundamentally, like if I've got a, let's say I've got a cube here, and I want to calculate the volume of that cube, you might remember that you would just take the 3 sides and multiply them together. So let's call that side x, that side y, and that side z. The volume of that cube or block would just be x times y times z. And so you'll notice that we've taken a length times a length times a length, and that's why we end up with cubic meters or cubic centimeters. A liter is simply a dedicated unit of volume, so that's why it doesn't have a cube to it. Density is the ratio of mass per volume. And you all have a sense of what it means to have something that's dense versus not dense. Density means you don't have to have very much of it before it gets pretty heavy, right? So something that has a high density has a lot of mass per volume. Whereas something that has a low density, you have to have a pretty big volume before you get a significant amount of mass. Let's try an example. So here we have a problem that says an aluminum block has a mass of 0.1728 kilograms. What's the weight in newtons to 2 decimal places? And if the block is 0.040 meters on each side, what's the density of the block in kilograms per meter cubed? Okay, so let's do the first part. We know that to calculate weight, it's just mass times g. And remember, g is 9.8 meters per second squared. And so I'll simply take my mass of 0.1728 0.1728 kilograms times 9.8 meters per second squared. And if you do that on your calculator and only keep 2 decimal places, you should get 1.69 newtons. So remember, when you take kilograms times meters per second squared, that is a newton, and so we can just replace those units with newtons. Okay, so that would be the weight of the object. Now let's figure out the density. We just learned that density is mass per volume. And so in this case, we know the mass, that's 0.1728 kilograms. And then for the volume, we're told that it's a block that has 0.040 meters on each side. So again, we know that if we have a block and we want its volume, we need to take the width of the block times the height of the block times the depth of the block and multiply them together. In this case, all of those measurements are the same. So you'd have 0.040 times 0.040 times 0.040. So if you do that math, you should get 2,700 kilograms per meter cubed. That is the density of aluminum. And the thing that's interesting about materials is the density is the thing that's the same. So in other words, if I have a very small block of aluminum or I have a big block of aluminum, the density is going to be the same. In other words, this would have less mass and less volume, more mass and more volume, but that ratio of mass to volume is going to be the same for each material. And that's why density is a useful quantity. You may remember that from chemistry, that you can actually identify what a material is by measuring its density. All right, let's do a quick check here before we stop this video. The question is, which has more inertia, a 2-kilogram bag of feathers or a 1-kilogram bag of nails? And the second part of the question is, which has a higher density? So think about these two questions. Maybe pause the video, and then we'll go over it together. Okay, so the thing that we always want to remember is mass is a measure of inertia. So to answer the question about inertia, it's just about which has more mass. So if we have a 2-kilogram bag of feathers or a 1-kilogram bag of nails, it's the 2-kilogram bag of feathers that has more inertia. Now, to get 2 kilograms of feathers, that's a lot of feathers. You'd need a really big bag, okay? Whereas a 1-kilogram bag of nails wouldn't have to be a very big bag. But if I've got 2 kilograms, that's more than 1 kilogram. So the 2-kilogram bag of feathers would have more inertia. Which has a higher density? Well, we know that metal is going to have a much higher density than feathers, and so the higher density would definitely be the nails. And you can imagine, again, to get 2 kilograms of feathers, you'd need a huge bag of feathers. To get a couple kilograms of nails wouldn't take a very, very big volume at all. Okay, in our next video, we will continue on and look at Newton's second and third laws.